stay on time, and I'll start with just a very brief introduction so I don't take too much of your time. But I want to introduce everybody in the class to our distinguished guest lecturer today, Courtney Roberts, who's joining us from the University of Minnesota, where she is an assistant professor and has built a really vibrant research program in organometallic catalysis. In particular, made some really important progress in the area of catalytic and stoichiometric difunctionalization of benzynes and related heteryne species. And I think her work really fits nicely into some of the themes that we cover in class. So it's a treat to have her with us. By way of background, she's a native Southern Californian. Were you actually born and grew up here, Courtney?
Yep, I was.
Where were you born specifically?
I was born in Redondo Beach,
Redondo
South
Beach.
Bay, yeah.
And stayed in Southern California for undergrad, where she completed her degree at Pepperdine before moving east to UNC Chapel Hill, where she carried out PhD research with Simon Meek, and then started her foray into colder and colder temperatures. First, taking up a postdoc position with Melanie Sanford at my alma mater, University of Michigan. Go Blue.
Go Blue.
Went to the other U of M for her independent career, University of Minnesota. And as I said, has gotten off to a great start. And we're really excited to hear from you. So I'll just give you the floor here. We have a 90-minute slot. You feel free to take as much time as you want. If we end a little early, that's also okay. And then, as per usual with guest lectures, we'll leave some time at the end if any folks have questions about career path, things like that, and that part. We'll crop the video, so if there's anything that you want to say just in private, don't want video record of it.
Sure.
Maybe like that. So take it away, Courtney, whenever you're ready.
All right, thanks so much. I'm gonna share my screen. Hopefully everyone can see it, and I'll use my laser pointer here. All right, so well, thanks so much for this invitation. And the opportunity to share with you about some of the chemistry in my group. So we are an organometallics group at the core of it. So I'm going to tell you two stories with some details I don't always get the opportunity to share. But since this is a class, I thought we could talk a little bit about things like ligand design and like fundamental principles like back bonding. So of course, I'm not the one who does the work. It's my wonderful group that does the work. So I always thank them first. They're really fantastic students. You can see we're outside in Minnesota, but people are still smiling. So I'm just really grateful for all their contributions. So many really fantastic ideas. They work really well together and they work really hard. So I'll try to point out the individual students on the slides that did the work, but I'm not going to be able to talk about all of our work. So I just wanted to acknowledge them from the beginning. And of course, we have to acknowledge funding. So the stories I'm going to tell you today are funded by the NIH. So hopefully for any of you students interested in going into organometallic chemistry and wondering where your funding can come from, really fundamental research can certainly, or has been able to be funded by the NIH. So in my group, we just really love benzyne intermediates. And actually, I tell people one of the reasons why I love benzyne intermediates is just like metals, they can react in so many different ways. So a lot of functional groups kind of have one type of reactivity, but benzynes, this is excluding any metal chemistry, but they can undergo nucleophilic attack. They can undergo multi-component reactions. You can actually insert into carbon-carbon bonds, which, oftentimes we need a strain and a metal to do. They undergo cycle addition reactions. So I was really excited about these intermediates because of just this profound have potential in synthesis. But I'm actually going to start the story out kind of telling you what's wrong with benzyne chemistry. And some of our solutions that come from organometallic chemistry, right? So everything I'm showing you here is strictly organic chemistry, which we love too in my group. But there's still a lot of challenges outstanding. So I'm going to kind of walk you through those challenges with this natural product synthesis of elliptocene. And one of the key steps, I mean, the synthesis is decades old, but one of the key steps actually goes through a pyridine intermediate. And so, you know, this gets them to the final product, which is fantastic. You can make the bond you want, showcasing how powerful aryne intermediates are, but there's a lot of challenges in the synthesis that I would say even to this day, you know, are still outstanding challenges, you know, even though synthesis is from the 80s. So the first challenge here is that aryne precursors are actually kind of difficult to access and use. So of course, this is a pretty explosive precursor here, and that's not a typo, that's not palladium, that is lead acetate to activate it. Certainly we've grown a little bit in terms of safer reagents, but their synthesis is still like quite challenging. And so I'm not going to have time to talk to you about this today, but I'll just give you just a brief one-slide overview of how we've tackled this challenge. So we decided to basically design an ideal precursor. So this is unpublished work here. But we said to ourselves, you know, how can we design an ideal precursor? Well, we want to make it in one step. We want it to be safe, and then we want to be able to derivatize it. So actually, we thought about this iodine like a metal, and we said, okay, we need to oxidize this iodine up to iodine 3. So we know a lot about redox chemistry from transition metal chemistry. We need to put what we call a ligand on it for solubility purposes and to get around some side reactions that happen. So actually, you know, despite this being a pretty organic project, we took a really organometallic take on it to get this precursor that you can make in a single step. And then you can derivatize it as well in a single step. This is less organometallic oriented. And then we're able to kind of be able to access arynes without things like lead acetate additives, but we can just use blue light to do this. So as I said, this is not really the focus of what we've done, but I didn't want to present all of the problems with benzyne chemistry that we see without kind of helping you understand. We're trying to overcome all of them. But the two problems with benzyne chemistry that I'm going to focus on today relate to organometallic chemistry. And so I sort of intentionally misled you by only showing one product in this reaction. The other issue with benzyne chemistry, right, is this is an unsymmetrically substituted benzyne. This is an unsymmetrically substituted 4+2 cycloaddition coupling partner. And so it turns out regioselectivity is a huge challenge in this field, right? So maybe if you're in med chem, you'd like a lot of products, and getting out 2 products is problematic. But of course, in total synthesis, this is not, you know, what we want out of our reaction. So there's a huge problem with regioselectivity. And so that's what I'm going to kind of cover first. But I'll just point out that third challenge that we see. You know, we probably should never have made that core through that particular 3,4 benzyne or pyridine intermediate, right? It's pretty electronically, it's not activated towards forming one product. So instead, we should have actually used this really electronically differentiated benzyne here, right? Nitrogen versus carbon, alpha to those 2 positions of the benzyne. And so then we would get a really selective reaction. But unfortunately, you can't make a benzyne in a 5-membered ring. That's an N or O heterocycle, right? You can imagine how strained that is. And so that's the second organometallic sort of solution that I'm going to talk to you about today. But I'm going to start out talking about some of these regioselectivity challenges. And the reason why I want to start with this comes really back to ligand design, which I'm sure you all have been studying a lot in this class. And, you know, the ability to use ligands to control things like selectivity is well appreciated in organometallic chemistry. So let's see what's going on in a free benzyne in this example that we just had. So why is it that we get about a 1-to-1 mixture of our 2 isomers? Well, Neil Garg and Ken Houck came up with this just beautiful model to understand and predict benzyne selectivity. So this is for pyridines or benzynes or any sort of hetero arynes that you might be interested in. And these groups can be anything. They can be in the ortho to the benzyne bond, meta. They can be, methoxy, CF3, electronically activating, and things like that. And so what they do is they intrinsically distort this triple bond of the aryne. And this is what is controlling selectivity. So it turns out that the nucleophile will attack the termini of the aryne bond that is closer to 180 degrees, that has more P character. And so that's where we get selectivity in this reaction. So the GAR group came out with a really beautiful way to override the inherent selectivity. So here's that 3,4 pyridine we just looked at. And what they saw was, the ratio is about 2:1 for addition at the position that is para to our nitrogen. And if we add in different groups like we see here, we can distort that bond away from linearity. We can start to reverse selectivity. We can also start to enhance selectivity depending on what group is there. So I think this is personally a really beautiful solution to this challenge of sort of leveraging substrate control. But in my group, we sort of thought to ourselves, what if a catalyst could control this reaction? All right. So here's an example where substrate control is doing great. Here we have this very activating methoxy group. So we get our product ratio 100:1 or 100:0, right? We don't see the other product. So, in some circumstances like pyridine, we would want a catalyst to control it. Sometimes we're just fine. So what happens to this distortion that's governing aryne selectivity when you add a metal? Well, it turns out you destroy it. You no longer have that distortion in that aryne bond when you're binding a metal, right? And this is because we have different rules governing selectivity, and we are no longer governed by that angle difference because our metal is sort of undergoing back donation into that triple bond, right? And so it's no longer having this distortion. So we see that we've completely destroyed the selectivity, right? And without a metal, we got beautiful selectivity with methoxy, but here it's roughly 1:1 with these coupling partners, right? So it turns out that, metal arynes are completely independent of the aryne distortion model. And so you might say to yourself, well, this is like a pretty bad place to start, at least with pyridine. We had some selectivity that we could enhance or reverse, but this is sort of where the idea comes in of using, everything around our metal center and our ligands to control selectivity. Because at the end of the day, while this is being eroded, we are actually controlling the selectivity, right? We're changing it from this aryne distortion model into something else. We don't know what the governing factors are, but that's what we're doing in this chemistry. And so you will likely have heard about and learned about allylic substitution reactions. So these are, beautiful names reactions that we see all the time in organometallic chemistry. We can have a lot of different allyl groups, starting materials, carbonates, acetates that we undergo oxidative addition in. And we get our allyl, this 8-3 allyl group, bound to our metal. In this case, I'm using an example of palladium. And in this case, what people like Andreas Falt and many others have leveraged these FOX ligands to do is really to selectively bind our allyl group. So we avoid a steric interaction with our C1 symmetric ligand with a phosphine donor and a nitrogen donor. And so, we sort of can selectively bind our allyl group in one way. And then we can use sort of a different organometallic principle of back to the trans influence or the trans effect to see that we have this palladium carbon bond is longer when it's trans to phosphine than when it's trans to nitrogen. So that weakens that bond and makes it the site of reactivity, right? So just by using C1 symmetric ligands, we can get a reaction that is both regioselective, and in this case, we have a stereocenter, so this is very enantioselective, right? And we can vary the R group on our oxazolene with, many amino acids and things like that, right? So at the end of the day, FOX ligands control the substrate binding through sterics, and then they control the site of reactivity through electronics. And so we thought this was actually a really perfect primed type of ligand system to be able to sort of translate this chemistry to arynes. So this is the team that worked on it. We have Aaron, Brylan, and Douglas work on catalysis, and then Alex and Nick and Sal work on some stoichiometric reactions. So I'm going to start with the stoichiometric chemistry first to help you understand sort of some of these principles and how we can tune our ligand design. And then I'll talk to you about catalysis and sort of the interplay of our substrate as well as our ligand and what it's doing to control regioselectivity in this case. So this was our hypothesis, right? We can think about having ligands that are different sizes, so a small ligand and a large ligand, so that we can favor one side of this equilibrium for how our benzyne is going to bind if we have an R group on it. And then we can have differentiated donors. One, for example, can be a phosphine, the other can be a nitrogen-based donor. And then we can start to leverage the trans effect for selective reaction, right? So these are just principles I'm sure you've learned in this class about ligand design, and nobody had translated this to benzyne chemistry, but we thought that that would work out really well. So first we started with the stoichiometric chemistry. So what Alex and Nick did is they formed a series of benzyne complexes with, in this case, we decided to go with nickel. We use nickel a lot in our lab. And so what we decided to do is we wanted to see how these bind based on sort of that steric and electronic environment. So using the cyclohexylphox ligand, we can see the major isomer is the fluorine sort of underneath the oxazolene side of the ligand where it's much it avoids any sort of steric interactions. And then we can make an isostructural series, just varying the different substituents, both electronically as well as sterically. And we can start to see the ratios actually change here. So, you know, it's not that you can bind a benzyne and it's always going to favor a major regioisomer to some extent. Of course, we have to think about electronics and the size of the group as well. And so we sort of see this spectrum here. And then we can start to think about a lot of ligand design principles. We can take away sterics from this oxazolene to favor binding. We could change from cyclohexyl groups to adamantyl groups, and that's exactly what we're doing to be able to favor a single regioisomer in this reaction. But the question is, what is controlling selectivity? I'll remind you, so we'll take this methoxy example that we'd seen before. So in this case, we get an 81 to 19 ratio of the methoxy complex where the methoxy is underneath the oxazolene. And previously we had seen methoxy as an example before, and we got the selectivity that's basically 1-to-1. So what is controlling selectivity? Well, it is the C1 symmetric ligand that's able to demonstrate this influence. But the different aryne substituents also change selectivity. So it's sort of an additive effect of our FOX ligand and our R group. So this is where I'm going to kind of switch over to some of our catalytic work in this reaction. Because catalysis, we can get a lot more data points so we can start to sort of understand and piece apart, you know, what is the additive effect in these reactions. So this is where Aaron and Brylan come in. So we're going to use these as aryne precursors. They form the metal through an oxidative addition. It's an intramolecular Suzuki reaction. So an oxidative addition, and then we're going to go ahead and do an intramolecular transmetallation with our B-pin. And that's how it's going to form in situ during catalysis. We're going to couple it with these bromobenzamides and form phenanthroidinone products. So Aaron and Brylan wanted to think about this in selectivity in terms of various different factors. Is it electronics? Is it sterics? Is it the ligand controlling? And we have all sort of descriptors to be able to understand this. So going back to that original idea in catalysis, what we're going to see is we're going to have a large ligand that's a phosphine ligand. It's actually going to be monodentate, unlike our FOX ligands, because oxidative addition is much easier. So it's a monodentate phosphine. And our small ligand is our acetonitrile solvent. So that's what we're setting up in the chemistry that I'm about to tell you about in catalysis. All right. So we went ahead and varied the sterics of our R group so that we can understand the influence of that on selectivity. So this is going to be an interplay of the ligand as well as, so a catalyst control as well as a substrate control sort of married together. And we can piece that apart using some data science. So we can have our different substituents on here based on the different size. And so what we're going to look at is the log of the ratio of these two regioisomers. You're going to see in the beginning, one is favored, and then depending on the ligand, we can actually switch to the other regioisomer being favored. And we're going to plot this based on the Charton value, which is going to represent our aryne sterics. All right. So we're going to go one ligand at a time. So when we use a small phosphine ligand, you'll recall I said that the phosphine ligand and the acetonitrile solvent is creating that C1 symmetric ligand environment. And we do see that we have a slope here, and this sensitivity value does show that we do have some dependence on the aryne sterics, all right? But when we add in different ligands of larger sizes, that's when we can tell if the ligand is influencing this at all. And so, of course, when we increase the ligand size, we change that C1 symmetric ligand environment, and much larger ligands give a much higher sensitivity value. And so we see that the ligand has a huge amount of control on the selectivity of whether you get A or B as our regioisomer. So this is an interplay of substrate control based on the substrate, the Charton value, as well as our ligands, right? So we do see that that ligand is able to influence it. So we can put this together and we can sort of plot different data points with different ligands, and we expanded our ligand scope as well to things that are smaller and larger. And we start to see that, we can put this together and get this linear regression to understand and predict the extent that sterics of our aryne and the sterics of our phosphine ligand are going to control this reaction. And so we tried many things: Tolman electronic parameters, cone angles, all sorts of ligand parameters, and this is what we found works best. All right, so what about electronics? This is only telling us about sterics and arynes and the ligand. We can do the same thing, sort of electronically varying our substituent there, and we start to see some clusters here. Again, when we plot this times our ligand descriptor as well as the sigma meta parameter, this represents aryne electronics as very well, right? So electronics and sterics and the ligands, the ligand amplifies both effects, right? So we can take these two charts and we can kind of do that linear regression that, is quite popular now, and we can understand that we can incorporate these into a single plot, right? And these coefficients are going to tell us, is sterics or electronics playing a much larger role? We see the ligand descriptor is a multiplier in both, so that has the most control in this reaction. And so we can go ahead and normalize this and solve this, and we see that the steric term contributes far more to regioselectivity. So now we know on our ligands, if the aryne sterics is the most important, we can bulk up our ligand rather than sort of playing around with a little bit more of electronic influence. So we can put this together and we can train a model, and we can start to predict things, and we can start to predict ligands that we might want to use in this reaction to get really good selectivity. So now that we understand each of these different factors as contributing to regioselectivity in arynes and a C1 symmetric ligand environment, we can start to, choose ligands. And so we can start to go from this reaction that I showed you in the beginning, right? This is not the same, this is a stoichiometric reaction, but using that same ligand with a C2 symmetric ligand, we see a one-to-one ratio, but here we can go ahead and predict that Trixie-Foss has a very large cone angle for the ligand descriptor, and so we can start to get really appreciable amounts of a single regioisomer, right? So this is an interplay between catalyst control and substrate control, but it certainly is the very first time that catalyst control in any form has been used in aryne chemistry, right? And this all just goes back to really fundamental organometallic principles, things like the trans effect, as well as sort of leveraging C1 symmetric ligand environments. So that's kind of the first problem I wanted to tell you about in benzyne chemistry that organometallics has been able to sort of solve, that the organic community alone, we didn't really have that option. Now, the second story I want to tell you about is the fact that, now that we know how to control the selectivity, that's great, but we never should have used this particular aryne because it's electronically and sterically not differentiated, right? We should have used this five-membered indoline here because that would have given us some, according to the aryne distortion model, some really great selectivity, but we can't make these compounds. So despite the fact that we can't make these compounds, my group sort of thought, what if we could, right? This is an important enough intermediate in synthesis that we should ask the question, what if we could, right? And I bring up all these drug molecules and agrochemicals, and we see a lot of these cores with these N heterocycles and five-membered rings. And I showed you the beautiful chemistry arynes can do, difunctionalizations, cycloadditions, sigma bond insertions, right? All of these types of reactions. And so we can think about building up so much molecular complexity on these intermediates if we had access to the synthon, right? So I do think it's worth pursuing problems that are deemed sort of impossible if the payout is important enough, right? And so we can kind of think about retrosynthetically the types of bonds that we could make, right? Not just maybe in the final product, but if you're a med chemist and you're on a campaign and you need to change up your aryl group, you don't know that the paratoluol is going to be best, right? In the drug Ambien, maybe you want to put an isopropyl group there or a methoxy group or a CF3, right? This is a great synthon to build these molecules up for libraries, right? We just need some organometallic, and then the other coupling partner, some electrophile like an alkyl halide. You can just think about, this amide being varied so much, right? This is a synthon that could be really useful to people. All right, so why don't we make these? Well, again, a really beautiful paper came out from the collaboration with Neil Garg and Ken Hauk and now Rob Payton. And they have this, what I think was pretty ahead of its time, model to predict whether you can make a benzyne or not. And so essentially what they're looking at is this energy of an aryne and the hydrogenation energy. And so what we see here is we see that they have these arynes that are accessible energetically. So indole and 3,4-pyridine, we saw this earlier. We can also look at examples in synthesis, and beautiful example from the Garg group in which this 4,5-indoline was used as an intermediate in natural product synthesis. I already showed you 3,4-pyridine being used, right, in ellipticine. So we can predict, we can use these, and then we can get in the lab and we can say, yes, we can make these compounds, right? So this is a really beautiful model that is, been validated time and time again. So we can move our aryne bond, we can, from the 4,5 position, we can make 5,6 indoline. This is predicted to be accessible. We can move it to the 6-7 position, which I don't have drawn, right? All these predicted to be accessible and validated experimentally. So really fantastic work on the computational experimental side. I'll come back to benzothiophene in just a second here. But what this paper does is it draws the line and it says, unfortunately, despite the fact we could have a 4,5 indoline or a 5,6 or a 6,7, we can never make the 2,3 indoline because it's just, as you can imagine, two strains, right? Having this aryne bonds in a 5-membered ring, right? We want triple bonds to be linear, right? 180 degrees to be sp hybridized. So we even have a change in hybridization in arynes that's a little different, but regardless, it's really challenging to have that. So we can't change the electronics of the R group. We can't, for example, change the protecting group to something. We can't add different electronic differentiators like in this 7-ase indole, or we can make 6, 5, 4, etc. Nothing that you do to this ring. You could take it away. You still can't make pyrrole as an aryne. We could change this fundamentally electronically from, a pyrrole-like nitrogen to a pyridine-like nitrogen. Nope, you still can't make these compounds. You can't swap out oxygen for nitrogen. These are all energetically inaccessible. The irony is actually benzyne chemistry was founded on this molecule back in 1902. Somebody predicted 2,3-benzofuran was an intermediate in a reaction. It was misassigned. I don't blame them. 120 years ago, it was hard to characterize compounds, but that's actually when people started thinking about benzyne. Now, the difference between benzofuran and benzothiophene and why we can access benzothiophene is these sulfur carbon bonds are longer than carbon oxygen or carbon nitrogen, right? That makes sense. It's a bigger atom. And so that expands the size of that ring so we can just about accommodate it. And this was actually an important insight for us as we thought about overcoming this challenge. So I only showed you sort of the idea of like there's a line in the middle, but actually it's on a spectrum of accessibility versus inaccessibility. So we're going to start our story trying to access the least inaccessible aryne here. All right. So I'm sure you all have seen Zeiss's complex in this class before, this platinum bound to ethylene. It's sort of a quintessential a molecule that most people teach about in their class, right? And it exemplifies things like back bonding, all right? So we see this ethylene here, for example, donates electrons into an empty metal d orbital, right? That's how most ligands bind. We see this all the time. I'm sure you've also learned about back donation. And so filled metal d orbitals can undergo back donation into pi star orbitals. And as soon as we start to add electron density into things like a pi star orbital, we start to break that bond a little bit, right? And so that's why we see these two ends and sides of this spectrum of a model. So the Duhrchat-Duncanson side of the model, where we have kind of weak back donation and near sp2 hybridized carbons in this ethylene. So the bond order hasn't changed that much, right? Maybe it's 1.8, 1.9, but it has changed a small amount. Versus a lot with early transition metals, especially, and some light metals, we see strong back donation and actually oxidation of our metal. And we really have changed that bond order significantly. And so when I was a graduate student, this concept like really fascinated me. I did rhodium catalyzed hydrofunctionalization reactions, and I would take my rhodium complex NMRs when they were bound to styrene, and I was really fascinated in the carbon NMR, how that hybridization changed. And that was really what inspired me to think more deeply about organometallic chemistry and how it can be leveraged for accessing things we might not be able to get our hands on, right? It was that observation when I was a graduate student that I just thought was a really interesting concept and a very different system that inspired this work. So does the Duhrchat-Duncanson model and metallocyclopropene, we like to call it metallocycloarene model, apply here? Well, we can take a look at the calculated value of a benzyne aryne bond versus the benzene bond, aromatics CC bond there. And when we bind our metals to it, we do see elongation, right? These compounds are very old. They're actually older than the 80s, and they've been known a long time. And so we do see elongation of that triple bond of that aryne. So these are very easy to make. It's just an intramolecular Suzuki reaction. So we do oxidative addition with your favorite nickel zero source or your favorite palladium zero source. You can use a monodentate ligand. In this case, you can use a bidentate ligand. You can use alkyl phosphines, aryl phosphines. This is a very easy reaction to do. Once you do oxidative addition, you have this nickel 2 complex, and then base is going to go ahead and add to our boron for an activation, just like in a Suzuki coupling, and we get to this nickel-bound compound here. So these are very easy to make. So going back to all of those arynes that we've never accessed before as synthetic chemists, and thinking and pulling from the organometallic principles of back bonding, our hypothesis was that all we need to do to access this entire class, and I've just shown 4 here, but you can imagine 100 5-membered N heterocycles and O heterocycles, that all we needed to do was just bind a metal, alleviate a small amount of that strain to be able to access this entire class of heteroarynes, all right? So this is a team effort here. Really, I just had some wonderful students. So Jenna joined my group. She switched into my group actually in her second year, and she really took off. And so she kept this project alive for many years when we didn't have the hit yet. And then she was joined by Roman and Aaron, who have both now moved on, graduated, or Roman was a postdoc. They really were a force to be reckoned with synthesis. They're excellent synthetic chemists. And then Sal was a huge help in our precursor synthesis, scaling the precursors up to 25 grams. And then Annabelle did some really nice preliminary work. And now that all of these students have sort of moved on to bigger and better things, this project is now taken on by Ali, Sanu, Douglas, and Sophie. And then we have a really wonderful collaborator, which I'm going to tell you about some of that unpublished work today, with Shuming Chen and our student Gabriel. All right, so here's a hypothesis, and a lot of people ask me, was this an accident? No, this was a very hypothesis-driven project. This is where we started. We thought that this would work, and we just needed to find the right ligand, we needed to find the right metal, we needed to find the right aryne for this. So we can make these aryne precursors actually in a single step. I told you that's a big challenge with the aryne world is making the precursors. While metal aryne precursors are much easier to make. You can just deprotonate with LDA and quench with isopropoxy borylane. And then we get this B-pen compound. As I mentioned, Sal has been able to scale this up to 25, maybe even 50 grams at this point. We can make a bunch of these, as you can imagine. That shouldn't surprise anybody. Moving the nitrogen around the ring, adding different groups and substituents, adding nitrogens. The synthesis is pretty straightforward. So we can go ahead and do this oxidative addition. I had mentioned earlier, you can do this with arylophosphines or alkylphosphines, monodentate, bidentate with 6-membered arynes, but we will learn that's not always the case with 5-membered arynes. The ligand really does matter a lot because so much back donation is necessary to form them. So we can do this oxidative addition, and then we try to add in our activator, and absolutely nothing happens. So these phosphines are in a trans relationship to each other. So they need to go through sort of an energetic barrier related to reorganization to put them in a cis position, as well as activation and transmetallation. And that is just too challenging. We cannot use triphenylphosphine as a ligand in this reaction. It will not form the aryne. But we can use a bidentate ligand that sort of locks our phosphines in a cis configuration that allows our group that needs to undergo that transmetallation to go much more easily because we don't need that reorganization of our square planar complex. So we can make this on a gram over a couple of steps, 56% combined yield. So here's a crystal structure. My students take a crystallography class, so we get dozens of crystal structures. And so we see this is an oxidative addition complex, nothing to write home about, right? This is pretty standard. We can see this carbon-carbon bond length is that of an aromatic ring. I'll point out some of the comparisons later, but this is not a non-remarkable compound. But what is remarkable is how we can use phosphine NMR to be able to understand what's going on in our reaction. So each of these phosphines is chemically inequivalent, and their communication to each other is the readout is our J value. So I'll point out this really beautiful Anne McNeil and Zimmerman inorganic chemistry paper here that talks so much about how we can correlate coupling constants to not only oxidation state of metal, but also how much donation that phosphine is providing. It's not a readout of back donation, so that's exactly what we need. We just need a readout of how much forward donation is here. So we see a J value of 28.5 hertz. And so according to this paper and all the correlations that they've done, if we form an aryne and we need a lot of back donation and a lot of forward donation from these phosphines, we should see a significant contraction of that J value. So that's going to be really important later. So I guess asked all the time, and because this is a class, I'll show you the results. What other ligands can be used? So as you can imagine, my group is an organometallics group, so we can do ligand exchange, no problem. So we can use a carbon backbone, DCPM, which is 1 carbon, 2 I've already showed you. We can use a 3-carbon backbone as well. When we get into this 4-carbon backbone with DCPB, what we start to see is some fluctuality in the NMR, and we see that our phosphines sort of end up being trans to each other. And so that problem with transmetallation that I talked to you about earlier is going to be a problem in this compound. And of course, we can do ligand exchange with arophosphines as well. So people always want to know the answer to this question, and yes, we can do ligand exchange in my group. So yeah, it's pretty easy. All right, so back to sort of our DCPE ligand that we've seen a lot. We wanted to see, can we actually make this aryne with this, right? Nobody's ever made one of these compounds before. We weren't really sure what to expect, but by the time we get down to the NMR, what we see in the phosphine NMR is these 2 resonances, and they have a very small J value, right? And this is indicative, as I told you, of how much donation our phosphine has. So whatever we've made over here requires those phosphines to be much stronger donors. And it did take us a while, but we were able to actually get this crystal structure. And this is the first example of accessing this class of inaccessible arynes. So again, because this is a class, I wanted to walk through a little bit about transmetallation, right? This is probably the most understudied fundamental organometallic step. You know, Scott Denmark and others have done some really beautiful chemistry, but we actually have an opportunity to almost freeze out an intermediate that's undergoing transmetallation. And we can learn a lot about that process. So we don't see any intermediate observed in our parent aryne complex, and so we decided to make it a lot more electron poor, so less nucleophilic, less likely to undergo transmetallation, and so we can monitor this by phosphine NMR. So we do see the aryne form right away. I will admit it is still a pretty fast reaction, but we could slow it down a small amount, all right? And so when we slow it down, what we see is this intermediate here that's forming, and I have this sort of inset here so you can see it a little bit better. We can see our J values are larger than that of the aryne, so it's likely not an aryne. And what we think it is this putative intermediate, which is actually the activated borate, that's sort of the snapshot of it right before it undergoes transmetallation. And so the reason it's broad is we can see some interconversion between the pinnacle oxygens and our tert butoxide. And so you can imagine that this phosphine trans to this oxygen, depending on what it's trans to, broadens out a lot, right? And so that's why we see that fluxional behavior. And then this phosphine is pretty sharp because we don't see fluxional behavior there. The other thing that we can kind of see in this reaction is we can monitor the byproducts of transmetallation. We see those grow in here over time, and we can see this intermediate here, which is very close to what the Denmark group reports in this science paper about transmetallation. So we're very confident that this is the intermediate that's undergoing transmetallation. So we don't often get to sort of trap this. I wanted to share that with you all. So going back to the idea, can we do ligand exchange? Yes, but can we do transmetallation with every ligand? The answer is actually no. All right, so I'm happy to answer questions at the end if you're interested in what these compounds go to, but the only things that undergo transmetallation to form our aryne are our DCPE, our 3-carbon backbone, and our DCPP, which is our 2 and 3-carbon backbones, right? We get beautiful full conversion to these compounds, all right? So this was quite an interesting thing. We really need to be careful with our ligand choice in this case. So what happens with palladium? I get asked this all the time, so it's kind of fun to talk to a class where I can actually show you some data that's unpublished. Well, it turns out we get stuck at this intermediate. Palladium does not want to undergo transmetallation. We can actually get this crystal structure of this transmetallation intermediate. And so palladium carbon bonds are longer, and I'll get into this. We can now do palladium, but this is kind of where we started out with. So nickel works a lot better in this reaction. So let's go back and understand structurally a little bit about these compounds. I want to talk a little bit about reactivity. So we can take a look at the calculated value of an aryne bond length and sort of measure up against our sort of Dewar-Chat situation that we have here with our C1, C2 bond length, and we see it's significantly elongated, right? So that back bonding is happening a ton in these compounds. It's not happening so much so that it matches that of this sort of boring oxidative addition complex that I showed you earlier, right? We have not elongated it so much so that it's a double bond, right? So it still has a lot of aryne character in it. But this arine character and sort of the extent of elongation of this bond gave us a little bit of pause, actually, because it's much longer than that of known accessible arine complexes. So actually, we thought we might be in a different place in this Durachat-Duncanson model to metallcyclopropene part of the spectrum. We might actually have a different electronic structure of nickel in these compounds versus accessible arynes. And this has the potential to be really exciting for reactivity, right? So part of organometallic chemistry is making trophy molecules, but then it's also understanding electronic structure and reactivity of these compounds. So how do these react? Well, they react. We can think about difunctionalization, right? The first reaction gets us to the sigma aryl complex. This is an intermediate in cross-coupling and Buchwald-Hartwig amination. So many different types of nickel chemistry has this intermediate here. So I'm going to focus in on sort of the organometallic chemistry of arynes. So these typically react as they have throughout history when they're bound to nickel as nucleophiles or alkynes, right? But I'll point out that the aza-indoline had a longer aryne bond length, potentially thinking about we might have some different types of electronic structure and reactivity. So does this react as a nucleophile? It does, right? It does have typical aryne reactivity. We can add in methyl iodide. It has a really a single regioisomer forms, and that's because the nickel carbon, this bond length is much longer, and so that's why it this nickel carbon to C2 is much longer, so it reacts selectively there in the principles we learned about earlier. We can react with other electrophiles, so aldehydes. Quite interestingly, we were expecting this iodine-3 reagent to undergo oxidative addition, transfer our trifluoroacetates, and undergo reductive elimination because we were thinking this was nickel 0, but instead the benzyne just reacts as a nucleophile and displaces a trifluoroacetate. So this was another indication the electronic structure of these might not be nickel 0, but it actually might be nickel 2, and they don't want to undergo oxidation to nickel 4, right? And so these sort of steps helped us to understand that we might have some pretty interesting properties with a nickel 2 compound. So if you add an electrophile, right, this reacts as a nucleophile, but if you add a nucleophile, this also reacts, right? So this is actually an ambiphilic molecule as it reacts with both electrophilic and nucleophilic sources of methyl. And that's because of the unique nickel 2 electronic structure. We can access other nucleophiles, sp3, that are more bulky. We can use sp2 hybridize, sp hybridize. We see some interesting regioselectivity changes here due to the stability of the product that's formed, the anion. So these are ambiphilic molecules. So why does this matter? Why do we care? Well, we care a lot about difunctionalization, and we care a lot about things like medchem campaigns. So if we treat this like a nucleophile, then we can get the reaction to go and just use a transmetalliting reagent to get to this regioisomer of our compounds. But if we just treat this like a nucleophile and switch the order of addition of our coupling partners, we can actually get to the other regioisomer. And so this will become important in just a moment, but this is pretty unprecedented reactivity for arynes. We can react with a lot of other coupling partners. We're doing things like fluorination and trifluoromethylation and cyclization reactions as well. So, these compounds have only existed since 2024. So I think there's a lot of types of reactivity that we don't know about. So in my last just few minutes here, I'm going to kind of talk to you a little bit about sort of the value proposition. Why can organometallic chemistry, what might seem some pretty esoteric molecules, how could that actually affect things in synthetic chemistry that we might care about, that might be useful to the world? Well, I'm sure you've seen medicinal chemistry talks where they talk about this design, make, test, analyze cycle. And so this really nice review by Pennington and coworkers kind of talks about some of the bottlenecks in this design, make, test, analyze cycle. Right, in the 1970s, they were taking ibuprofen. That's a pretty simple molecule. But his point is that complexity has increased. In the 2020s, you're taking Paxlovid, which is the active ingredient of it, right? So over time, this, make step in the design, make, test, analyze cycle has gotten longer. And due to computational tools, we've gotten shorter in our other steps, right? So how do you develop a drug? Well, we can think about things like nitrogen scanning. So this is another Pennington review in which they highlight this molecule from Amgen, this kinase inhibitor, in which all they needed to do to improve potency was add a nitrogen at the 7 position. All right. And we see a 300-fold increase in potency. So how did they have to do this? Well, of course, they needed to make all of these individual molecules, right? We see we actually get worse when we have a nitrogen at the 4 position, a little better at 5, a little better at 6, but really we had to make all this series of molecules to be able to understand that the nitrogen at the 7 position was the most important. All right, so how would we do this? Well, I think you all probably take a really beautiful heterocycles class and learn all of these named reactions. And we can think about all of these different components that we build them up from, right? So if you wanted your kinase inhibitor to have, 2 different functional groups here that were the same, and you wanted to swap your scaffolds here, we would do that right through these really nice named reactions. But this does take time, right? So here's an example of a difunctionalized indole-like core in which we've moved from an aza-indole to indole to a furopyridine to another aza-indole. And we see that, we had to start from different starting materials and it took a different amount of steps, right? So this is actually a real challenge in medicinal chemistry. But, what if we had a new functional group that, we could introduce to MedChem that they haven't had access before, and then we could start to think about using a common set of coupling partners. What could we do with a new functional group that just existed since last year? And this is sort of where we think about this chemistry on the medicinal chemistry side of things. So I showed you the spectrum of inaccessibility of arynes, right? And I showed you a single molecule in this entire part of the presentation, right? But what about all the others? What about indoles? What about benzofuran? I told you that was the first one they'd ever tried to make. What about all of these? And what about the other ones I haven't even showed you, right? 4-aza-indole. We can make 6 or 7 aza-indoles far more accessible. Can we make these compounds? Can we realize this sort of like universal new synthon? Well, this is going to require some organometallic chemistry. So we can make a bunch of these, right? We can access a nitrogen at the 7 position. We can add in more nitrogens. We can add in groups, move our nitrogen around. But what you'll notice here is that 4-aza-indoline is missing. All right, so what happens with 4-aza-indoline? Well, it turns out that we get stuck at this borate intermediates, right? I showed you that transmetallation pathway, and we never can overcome the energetic barrier to get the aryne to form. So this is highly problematic if you want to have a universal synthon. It can't just work for some things and not for others. But of course, we're organometallic chemists, so we just need to understand what the problem is and design some more ligands to overcome that challenge. I'll also share with you, it's not an electronic effect really. When we put our nitrogen back in at the 7 position, like we've seen work this entire time, it still forms this borate complex. I showed you palladium already, and we see what happens with this benzofuran also gets stuck there. So why is this? Well, if we look at the energetic profile of something that does work, what we see is this intermediate is actually pretty low energy with our 7-aza-indole. Then we have a very reasonable transition state barrier of 22 kcal per mole, and this happens at room temperature. And there's 2 interactions that I want to point out. First off, we have our borates sort of steric interaction with our N-methyl group. And then we also see these cyclohexyls interacting actually with this CH bond there. All right, we don't often think of CHs as sterics, but this is what we see. And then it turns out that the indole is actually quite stable. All right, so let's take a look at what happens when we can't form an aryne. So when we have, instead of a 7-aza-indole, we have the 4-aza-indole, we've lost one of those interactions. It's missing. So we can no longer overcome this energetic barrier. So it isn't that much higher, but when you start to heat these, they start to proto-deborylate. So that's not the solution to this, all right? So we can kind of look at these transition state structures from Shuming Chen and her student Gabriel, and we can kind of see some of the carbon bond lengths are much longer, and so that's why we can't make our 4-aza-indoline. All right, we can kind of see it a little bit better here. We see no sort of steric interactions that is going to help that transmetallation. We can see it kind of stuck at this place. All right, so there's no driving force. So, are we sure it's not electronics? Well, we can kind of see that interaction is present in all the ones that do form benzene. We see those barriers are all pretty reasonable for room temperature. All right. We can also see these carbon bond lengths are all pretty much the same for things that work versus it's much longer when it doesn't work, right? We don't have that steric clash helping to that sort of that transmetallation. So what's going on in our benzofuran? Well, instead of missing our CH interaction, we have that, but we no longer have the steric interaction with our methyl and our oxygen in our benzofuran, right? And that's why this is not overcoming that energy barrier. We don't have that sort of push for it to undergo transmetallation. What about palladium? Well, we have these interactions, but they're just much smaller because our palladium carbon bond lengths are much longer, right? And this is because palladium carbon bond lengths, it's a different mismatch and orbital overlap. So this is why palladium does not work. All right, so this is kind of a challenge. If we have all of these arynes that won't form, but we really want this universal synthon, what do we do? Well, we're organometallic chemists, right? So it's actually a really simple problem. We just need to increase the steric interactions between our arynes to allow that transmetallation to go. And how are we going to do that? We're going to play around with things like bite angles. All right, so there's a reason why I told you earlier in the presentation, we can use other ligands that will undergo transmetallation. So here we've increased the bite angle in this reaction, and it actually goes faster into to fuller conversion than when we use the 2-carbon backbone. So that's all we need to do. We need to change that bite angle, and now we can increase those interactions on all of these, and just a small amount of understanding organometallic chemistry can enable us to do this reaction. So we asked Shuming to run these calculations, and we see that energy barrier is much lower when we've increased the bite angle. And so now we can get full conversion to all of these arynes in all cases, just by switching from a 2-carbon linker to a 3-carbon linker. So when we think about that sort of universal synthon, we can now start to fully realize this and think about common coupling partners where we could just change our heterocycle and we can get this wide variety of products, right? We needed to understand a lot about organometallic chemistry to get this to work, but that was pretty easy. We can understand those things. Also remind you, these are amphiphilic molecules. So you can start to think about doubling the number of molecules in your library, right? Just by switching the order of addition of our coupling partners, we could do that. And then finally, we can start to access oxygen heterocycles, as well as think about the reactivity that palladium might have here. So this is our idea, is getting to this common functional group and sort of, in process chemistry, all these named reactions are still going to be used, but we'd really like to speed up that design, make, test cycle through this new synthon. So in summary, we can prepare these precursors in a single step. We can just use really fundamental principles that you all learned in this class of organometallic chemistry to access things that were previously inaccessible. And then finally, we can, this was a perchance that these are amphiphilic, right? We didn't know that from the get-go. And so we can explore that and really leverage it to use a lot of different coupling partners with these intermediates. And so with that, I showed you the students as we went through, but it's always good to thank them again for their tremendous work. And thanks so much for the invitation. I hope you learned something about organometallic chemistry. All right.
Awesome, Courtney. We'll open things up to questions. Several. Sebastian, do you want to start?
Thank you. Great talk. I was curious at the beginning when you were kind of talking about the unpublished hypervalent iodine chemistry. Does that also work on heteroarynes, or is that only for carbocyclic?
Yeah, that's a great question. Yeah, that is definitely where we're going next with that. So because the chemistry is not an elimination reaction, so it's the first time that an aryne reaction has been, or an aryne precursor has been activated with blue light. And so it's actually goes through homolytic cleavage of the IO bond, and then you're getting a radical cascade reaction to form the benzene. And so, the arine model that Neil Garg and Ken Howe came up with says you can't do the elimination, but I do think it's very possible to do heteroarynes using these light activation conditions. So that is definitely somewhere that we're going, but we have not made them yet. We've ordered the stuff, but we haven't made them yet. But I do think it could overcome some of these challenges.
Thank you.
Mm-hmm.
Yeah, and I'll just say too, if anyone is joining on Zoom wants to ask a question, please just put it in the chat window or raise your hand if you want to unmute yourself. Here.
Fantastic talk. Thank you so much. I just wanted to ask, maybe it's a naive question, but for your transmetallation step, where you mentioned that that complex gets stuck on some occasions and larger bite angle helps with that. Have you guys considered also, instead of going from the boronate complex, maybe investigating, I guess the bond length is larger for carbon silicon, but potentially the silicate, seeing as it's pentacoordinate, would be another option, and you could make that the same way. So maybe with TBDPS chloride, for example, would that be something that you guys have investigated or are interested in investigating also?
Yeah, totally. I love that idea. Once we figured out that it's the transmetallation and that sort of need for sterics, that's absolutely, I think you're thinking right in the correct direction. So yeah, so one of my students has made those compounds and we're trying to see. But truthfully, actually, CH activation, if that was a CH bond, is another thing we're investigating through like a CMD mechanism with an acetates. And that's actually proved because it's a different mechanism, rather than a transmetallation, it would be a little bit more like just an X-type ligand binding. That's another route that we're going down that's shown some promise. So I think silicon's a great idea. We've also done the calculations. If you just change the boron protecting group to change that steric environment, that also works quite well to help that transmetallation. So you're absolutely on the right track. I think that's a great question.
Thank you.
Mm-hmm.
Any other questions at the moment? Anything over Zoom? So Courtney, you hinted at how to turn on reactivity with palladium.
Yeah.
I don't remember seeing that published so far. So I'm just curious if you are willing to share the secret sauce or just maybe a general picture about how you've gone about that.
Yeah, so the palladium complex is it's just like much harder to isolate. So because those carbon palladium bonds are much longer, I think that it's pretty reactive. They're pretty weak bonds. So we start to actually get things like trimerization of the arynes, which is a known reaction with transition metals. So it's really more it's not published because we can't get it clean yet. We know it's formed. We can look at the phosphine NMR and the carbon NMR, but we're just having our trouble getting our hands on it, to be honest. So yeah, so we haven't investigated the reactivity of it yet because yeah, we're just, we'll get it. It will take a little while, but it's just far more sensitive. But I think that means that it's going to be better for catalysis, right? That's sort of like, if it's unstable, then it's going to be great for catalysis. So I sort of showed the stuff in the beginning, our palladium catalysis with 6-membered benzynes in the beginning. And we think it'll translate pretty well with the 5-membered arynes and palladium. So we're hoping the instability like actually pays off and it's better for catalysis.
Those pre-transmetallation complexes are beautiful, by the way. I don't.
Thank you.
You
Yeah.
probably know this better than me, but it's, if I'm remembering right, there's fewer than like 5. I mean, there are 5 complexes that are crystallographically characterized out there in the literature. Some of them are like model complex, not actually reactive. They're just
Yeah, we were pretty excited about that, to get that like snapshot of like transmetallation and actually like be able to look at bond lengths. And it's actually not what is reported in the literature. Is most people say it's the activator that's bound and not the pinnacle oxygen, but that's not what we crystallize out. So there are some slight differences, and I'm sure in the literature that's probably true. So I think maybe transmetallation is, yeah, we can open it up a little bit more and just study that actually, because not that much is known about it. So we almost lucked out. That was, again, sometimes serendipity is a good thing. You can study more fundamental chemistry from that.
Could you comment on the role of activator there? It looked like most of the examples you did were with like TMaloxy.
That's a great question. So other activators work. It's just so soluble. It's a solubility thing. So it's so soluble that the activation happens basically, instantaneously, because it's a pretty low energy complex after it's been activated. So it's just a solubility thing. You can use other alkoxide activators. I think you can even use fluoride, but the sterics don't really help that transmetallation. It's a solubility thing. So we were using terpentoxide and we were getting it, but it was a little unclean because it does react with nucleophiles. So you would form like 50% would convert to aryne, and you still had terpentoxide coming into solution, and so it would react with the aryne. We now understand a lot more about concentration, so we can go back and use terpentoxide or methoxide, and it's totally fine. But at the time, it was really a solubility of the activator so that it didn't react with the aryne. That's the secret of why we used it. I think that's in industry, you see it all the time because of the solubility profile.
Fluoride would be a cool one if you could get the complex, because I think this role of fluoride has been invoked pretty commonly, but then it gets to this point that you raised where then people are saying, well, the activator needs to be bound when you're making the 8 complex.
Yeah.
Fluoride is going to be non-polarizable and small, so it's not. So it could kind of settle that as how it could be involved in transfer.
Yeah, so we do have one fluoride activated complex. It's with pyridine. It's a 6-membered aryne, but it has crystallized out. So I agree with you. That's quite an interesting question, right? And we also think in Suzuki couplings, quite often everyone's like, well, the pinnacle gets hydrolyzed off all the time, and this is like water-free. So that's also not necessarily true in all cases.
I think Scott Denmark and Matt Sigmund have been pushing back on that with some of their stuff, right?
Yeah. So I think I would say transmetallation is just oversimplified in the literature. I think there's a lot more that we need to figure out about. But yeah, we're excited about this fluoride complex, just to be able to have seen it, and it does not undergo like facile transmetallation. So, but that student graduated, so I need to figure out what to do with it. Yes.
Yeah, they're scientific questions. We also promised we'd have a few minutes at the end for any kind of career-related questions, and maybe I can kick that off with just a general one, which is